All right, you guys, today's all about shortcuts. I'm going to show you how we can do these calculations without using a z-score chart. We're going to be using our graphing calculator today. So language, we know that a percentile divides our distribution into 100 equal parts. If we say that you fall in the 70th percentile for height and you're an adult male, that means that you would be taller than about 70% of other adult males. Deciles, we know that that's 10 equal parts. Quartiles, quarters, 4 equal parts. And the IQR is the middle half of our data, the middle 50%. To get that figure, we're looking at the Q3 minus the Q1. So we're essentially trying to say how spread out that middle half of data is. Okay, we've been using the z-score formula for a while. We know that it's just the observation, whatever the context is for our data, minus its mean over the standard deviation. Okay, we also know that if we want to solve for x instead, right, that's our observation, we get a new formula that gives x in terms of z. So to do that, right, we clear our fraction, multiply each side by the standard deviation, right, that's really 1 to 1 right there. So I know that my z-score times my standard deviation is going to be my observation minus the mean. And I want that observation by itself, so I'm going to add the mean over to the other side, and I get this new formula. My observation equals my mean plus my z-score times my standard deviation. And that should be pretty intuitive because we're saying build off the mean. We want to be so many standard deviations above or below. Okay, so now the shortcuts that we're going to see in our calculator. Let me slide this up, zoom in a little bit. So when we start using our calculator, we're going to see these different functions show up. We're going to see normal PDF. So that just stands for a probability density function or distribution function. And we use this to graph a normal curve. We're not going to be using this in our class. We're going to be using this second one, CDF, normal CDF. We're going to use that a lot. So that's the cumulative density or distribution function. So this enables us to produce the cumulative probability or cumulative area from a lower boundary to an upper boundary. What we type into the calculator is normal CDF, lower to upper boundary, the mean and the standard deviation of our distribution. Sometimes we know that, and sometimes we're using z-scores instead. So if we know the mean and standard deviation, so for example, if we're looking at adult male height, my mean is 70 inches, my standard deviation would be 4 inches. So I would just say use the mean and the standard deviation for my data set. Okay, if we're using z-scores instead, we'd use just 0 and 1. So we know that the mean, if we're talking about a z-score value, z is 0 because we're 0 standard deviations away from the mean. All right, we're going to use inverse norm. We're going to use that a lot too. So that's essentially when we're going backwards. We're saying this is the inverse normal probability density or distribution function. So this produces the x value or the z-score at a given probability based on the mean and standard deviation. You'll see what this looks like in context in a moment. So when I type this in, right, inverse norm, I'm going to show the proportion below, right, the region that falls to the left. Okay, some fancier calculators, we can specify what region we want it to be, but most of our calculators are doing that lower left-hand tail. And then we tell it that this is the mean and this is the standard deviation. If we know it, for example, adult male height, again, could be 70 and 4 for those values, or we could be using z-scores 0, 1. Okay, so let me show you what that looks like in context. So let me slide up. And let's take on that first example. I'm going to get it a little bit tighter. Let me just adjust. Okay. Let me get zoomed in. All right, so for all of these, we're going to be using our calculators now. We're going to move away from a z-score chart. So here I'm saying I want it rounded to the nearest 4 decimal spots. So here I want, where is z equals negative 1.5? So first I'm just going to put that little marker here for the mean. That's a z-squared of 0. So negative 1.5 would be about right here. Just giving myself a visual anchor. And then I want the region that is to the left of negative 1.5, that lower left-hand tail. All right, so when I type this into my calculator, I need to tell it a region. And over here, this lower left-hand tail really extends for quite a while. So we need to say a placeholder for negative infinity, right? I can't type negative infinity into my calculator, so we just need a number that can be a good placeholder. So when we're talking about z-scores, we use negative 99 or something that, again, is just a placeholder for negative infinity, something that is so far to the left, right? It would be so impossible, essentially, to have a z-score that is that far out to the left. Okay, so when I type this in, right, I'm going to do normal CDF, so I'm going back to my distribution, second farce. Okay, I want normal CDF, it's my second choice. Right, PDF would be if we wanted to graph a normal curve. We're not doing that. So here's normal CDF. It's going to ask me for my boundaries, lower and upper. And I want here from negative infinity to negative 1.5. So I'm going to use my placeholder. Right, the calculator is giving me one, but I'm just going to give a different one. So I'm just going to say negative 99 up to negative 1.5. And I am using my mean of 0 and my standard deviation of 1, because here I'm given a z-score. Okay, I want to paste it, and here's what it looks like on my home screen. I hit enter, and it gives me the area that falls in that space. So let me just a recap of what I said. So here's normal CDF. Right, my lower boundary, I used negative 99, right? It's my placeholder for negative infinity to negative 1.5, mean is 0, standard deviation is 1. So here again, lower upper, mean, standard deviation, and I'm getting about 0.0668, so I'd say 6.68%. Okay, next one, let me slide that over. So here I'm saying, well, what about when z is greater than 1.5. So again, I'm just going to plant my mean down, z-score is 0, and put where z is exactly 1.5, or at least I'm just trying to give myself a visual anchor, and then I'm looking at where is it more. So I'm just going to shade that region right here. I want that upper tail. Now I know it's going to match the calculation that I just did. I just want to get you used to how the calculator works. So here, that upper tail over here, right, I'm looking at my placeholder for positive infinity. And again, when we're dealing with z-squares, we just use a nice placeholder. I'll use positive 99 this time. So we've seen in our examples, we really haven't seen anything that is more or less than a z-score of negative 3.5 or positive 3.5. So we're just picking a number that is very much farther than those two extremes, right? So it's just capturing all of those unusually high or unusually low instances. So when I type this in, let me just write it out first, and then I'll show you what it looks like. So normal CDF, we're going from 1.5 to 99, again, placeholder for infinity, mean of 0, standard deviation of 1. All right, so back to my calculator. I'm going back to my distribution, second farce, normal CDF. Now I'm saying I want from 1.5 to 99, 0, 1, paste it in my home screen, and voila, right? I see the same probability, which makes sense because those have the same magnitude, what we saw in A and what we saw in B. A z-score of negative 1.5, right, that lower tail region, and a z-score of 1.5, that upper tail region. So about 6.68%. Okay, so now here are all of our unique variations. So we're looking at the ones that read as a magnitude. So here for C, right, I'm saying that the distance from the mean, right, here's my mean, z-score is 0, is greater than 2. So if I look at my mean, I go up 2, right? Here's the z-score of 2, down 2. Here's my z-score of negative 2. And I'm saying more than 2 away from the mean. So I'm looking at my tails here and here. Now remember, again, that over here is negative infinity. Here's positive infinity. And my placeholders for that are going to be negative 99 and positive 99. Okay, and again, I just have to find 1 because I know that those 2 regions are going to match. And then I just double it to get both of those tails. So here I could say normal CDF, negative 99 to negative 2, 0, 1. So here I'm going to type that in. Okay, so back to my distribution, second verse, normal CDF, I'm saying negative 99 to negative 2, and again 0, 1. And it gives me 0.0228. And I know that this area and this area are going to match, so I just have to double it so I can multiply it by 2 or add it to itself. And I get 0.0446, which is about 4.46%. Okay. Over here is one of our special variations. So here we're saying that our distance from the mean is more than negative 2. I can also conceptualize it as absolute value bars, right? I know that something forced positive is always going to be greater than something negative. You've heard me say that a lot. So that really encompasses everything underneath our curve. No matter what I plug in here for z, it's going to produce a true statement overall. So we know that this is going to be 100% of the time. Right? Again, a number that is forced positive, it's always going to be greater than something negative. A distance will always be more than something negative. Okay, another variation right here. So magnitude, where is the distance from the mean? Where is it less than 2? All right, so less than 2 standard deviations. So again, I'll just make a marker here. Negative 2 to positive 2. So z equals negative 2, z equals positive 2. So where is it less than 2? So imagine you're standing here at the mean. You go 2 units up and 2 units down. Anything that's in between this region is going to be less than 2 standard deviations from the mean. So we're looking at that in-between space right here. All right, so again, we're doing normal CDF. We're saying from negative 2 to positive 2, and we want to use 0 and 1, mean and standard deviation. Okay, so going back to my distributions, normal CDF right there, and I'm saying from negative 2 to positive 2, 0, 1, paste it, and there we go. So 0.9545. Or 95.45%. All right, last variation. Here again, back to magnitude. So here we're saying that the distance from the mean, the magnitude, is less than negative 2. Well, how could I have a distance that's less than something negative? I know that that's impossible. I also know that a number forced positive can't be less than something negative, right? So I'm not shading any part of this curve. This would occur 0% of the time. There's a 0% chance of this occurring, right? Again, a positive number here cannot be less than something negative. So a couple ways we can conceptualize that. All right, flip it over to the back. All right, so now here I'm saying find the z-score that corresponds to each region. So we're essentially working backwards. So if I say the 6th decile, just remember that that means the 60th percentile. So I'm looking at where do I have 60% here to the left. So here I know that that area below, that area in that lower left-hand tail, right, again, area below is 0.6. So when I type this in, I'm going to say inverse norm. I'm going to tell it the proportion that's in that lower left-hand tail. The proportion below is 0.6. I'm going to give it the mean of 0, the standard deviation of 1, because I'm asked for the z-score. And it's going to pump out the z-score that corresponds to this proportion below. All right, so inverse norm to get there, I'm just doing second varse back to my distributions, third choice this time, right? The area, these calculators are saying proportion below. So we type in 0.601. Paste. It's going to give me the z-score that goes with that region. So 0.2553. Oh, I think I said that wrong. 0.2533. That is the z-score that goes with that proportion. Now, some of these fancier calculators that we've been using in class, we can specify what region we want. So if I go back to my distributions, and I go to inverse norm, here we see an extra feature, right? It's saying, well, which tail do you want to use? So here I'm saying, well, 6th decile is the 60th percentile. So I'm looking at 0.6 is my area. My mean is 0. My standard deviation is 1. And I'm saying I want that left tail. Now, our other calculators that we use, they're assuming that it's the left-hand tail. What's nice about these newer ones is that we can actually specify whether we want the region that's in the middle or the tail end that's to the right. So here I'm going to say left tail. When I paste it, right, this is what it looks like on my home screen. I hit enter and it gives me that same calculation. So 0.2533. All right, so next up, I'm saying, how about the top 18%? So here I'm looking at, well, what's that top 18%? So let's shade an approximation. So here's that top 18%. We know that if that's the top 18, that's the same as the bottom 82%. So here I could think of this, if I'm using one of those older calculators, I could say inverse norm, 0.82, 0, 1. So let me show you again. So back to my distributions, inverse norm, 0.82, right? Again, these older calculators, it's always that proportion below. Mean and standard deviation are always there. We paste it, and it's going to pump out the z-score. So 0.9154. But on these newer ones, I'm not going to keep showing this to you, but I'm going to show it to you just one more time. So on these newer ones, right, I could do it like this. I could say, okay, back to my distributions, inverse norm. Here I could say, well, I know that that area that was above in that upper right-hand tail was 0.18. So I can say 0.18. Mean, standard deviation are set, and I can say, well, that's the right tail, the upper right tail. Paste it, and you can see that it gets me the same end result. So these newer calculators, they can do fancier things. They can get to that solution just a little bit faster. All right, next up, the middle 70. So if I shade the middle 70, so maybe about like that. Okay, so that means that I have 30% left over. And if I split that 2 ways, I have 15% in each tail. Okay, so if I want this z-score, I can say inverse norm, 0.1501, just like that. So 0.15. And we get a z-score of negative 1.0364. Okay, now this one is going to be its positive counterpart because they have the same magnitude, right? Because right here is 15% in that lower left tail and 15% in that upper right tail. So I don't even need to plug that in. Okay, let's say that I just wanted to double check that. Right here, this would be 85% to the left. Let me just retrieve that previous one and make that 0.85. You're going to see that positive counterpart right there. So there we go. Okay, and then lastly, let's say that we're looking at the markers for the IQR. Remember that that's the middle 50%. Okay, so if that's the middle 50%, then I'm taking the remaining 50%, splitting it two ways, and I get 25% here and here. And I want those markers here and here. And again, once I find one, I actually know the other one too. All right, so here I would say inverse norm. Proportion below is 0.25, mean of 0, standard deviation of 1. All right, back to my distributions. Inverse norm, 0.25, 0, 1. Boom, here we go. So we get a z-score of negative 0.6745. And we know the other one will be its positive counterpart. Again, we have the same proportion in each of those tails. So if I know one, I know that this one will be the positive counterpart. All right, so those are some fundamentals and then one problem that has concrete data. All right, so here, let's see. Okay, so our situation here, we're looking at babies. We're looking at baby girls, and we're told that the weights of a given age and gender are approximately normally distributed. And we're told that this context has a mean weight, 12-month baby girl, has a mean weight of 21.25 pounds with a standard deviation of 2.2 pounds. So I'm just going to summarize that right up here. So 21.25, comma 2.2. Okay, so here now, again, now I have data, right? I'm not just looking at z-scores. So here I have data that's going to actually help me move faster. So what is the percentile of a 12-month baby girl who weighs 19 pounds? Okay, so again, I'll just visualize this. It's not required, but it just helps us to see what we're solving for. So if we're looking at a 19-pound baby girl, we'll say, okay, well, that looks about right here, right? Because my mean is 21.25 pounds. So here, if I want to figure out, well, what is the proportion that falls in this region, and then round it to the nearest percent to make it a percentile, right? I'm trying to capture from negative infinity up until this marker here, where we know that that is 19 pounds, right? 19 pounds. So here my placeholder when we have data, right, I usually pick something that's just a little bit bigger. So I like to use negative 9,999, which is totally fine, right? It's totally here. It's pretty much impossible to have a baby girl, right, that would have a weight that's anything negative. But again, just to have good habits, we're going to say something that's so far to the left, right, that it's something that we know is going to cover every single possibility. So we're saying from negative infinity, we're just using a placeholder, up to 19, right? We want to capture all of those possibilities that fall in that space. And then we're using this mean, this standard deviation. So we're going to say normal CDF. From negative infinity, here's my placeholder for that, up to 19 pounds. Mean is 21.25, standard deviation is 2.2. All right, so we're going to plug that in. So back to our distributions, normal CDF, we're saying from our placeholder here, negative 9,999, up to a 19-pound baby girl. But now we know that our mean is 21.25 and our standard deviation is 2.2. So it's going to give me the proportion that falls in that region, 0.1532. And I just make that the nearest percent, right? Percentile. So 15.32% would mean, oh, that's about the 15th percentile. So just round to the nearest percentile. So 15% of 12-month-old baby girls will have a weight of 19 pounds or less. Okay, next, here, what percent of 12-month baby girls weigh more than 20.5 pounds? So more than. So again, here's my little anchor spot. There's my mean. This is going to be a little bit below it. So right about there, we'll say that's where my data point is, the 20.5 pounds. And we're looking at more than that. So again, I'm trying to capture the area, right, the proportion that's above this marker. Upper tail, right, here's infinity, positive infinity, but my placeholder, again, I'm just picking something that is really big, right? So 9,999, and then I'm saying normal CDF. Okay, from 20.5 to my placeholder for infinity, 9,999. My mean is 21.25. Standard deviation is 2.2. All right, plugging that in. All right, so back to my distributions, but now I'm saying 20.5 to 9,999, 21.25, and 2.2. All right, so I get 0.6334. So 63.34%. Okay. All right, next one, C. What percent of 12-month baby girls weigh between 20 and 22 pounds? So again, I'm just picturing solving for a percent, right? The proportion that falls in this region. Here's my mean. Let's say that I make a little mark here for X is 20, and here is X is 22. Right, I want to capture that proportion in that region right there. So my keystrokes here would be normal CDF, 20 to 22, mean 21.25, standard deviation of 2.2. I'm just going to tell you what it is, 0.3485 or 34.85%. All right, so those are, again, the shortcuts for when we're solving for a proportion that falls in the lower tail, the upper tail. For those cases, we need a placeholder for the infinities. Otherwise, we're trying to capture a space that's in between a lower and upper boundary that are clearly stated. In our next examples, we're kind of going backwards, right? Because we want to solve for the weight when we're given a proportion that falls in a certain region. So here I'm saying, well, what weight corresponds to the 60th percentile? So here's my mean, and here I want to solve for the X value that creates this situation where there's 60% that falls in that below, that lower left-hand tail region. So here I would say inverse norm, 0.6. I do know my mean, 21.25, and my standard deviation of 2.2. So now it's not going to pump out the z-score, it's going to pump out the observation because I'm telling it what the mean and standard deviation are for this particular distribution. So I'm saying second varse, inverse norm, area below, proportion below is 0.6, 21.25 is average weight with a standard deviation of 2.2. All right, so it's going to say that would correspond to a weight of 21.8074 pounds. do a couple more and then I'll close it out. All right, what weight corresponds to the first quartile? So the first quartile, right, that's really the 25th percentile. I'm solving again for a weight. So if I want to visualize it, again, here's my mean. So I'm looking at where would I have about 25% in that lower left-hand tail. Right, I'm trying to figure out what that x value is, what that observation is. So here I'm saying inverse norm, 0.25, 21.25 is the mean, 2.2 is the standard deviation. Okay, and it's going to pump out the weight that corresponds with that first quartile. All right, so back to my distributions, inverse norm. I'm saying 0.25. My area mean are already set. Enter. I get a 19.7661 pounds. Okay, let's see. Next one. How about third decile? So third decile is going to be the 30th percentile. So I'm looking at 30% here to the left, that lower left-hand tail. And I'm solving for the observation that goes with that. So again, it would be inverse norm, 0.3, 21.25, 2.2. Right, it's going to pump out an observation of 20.0963 pounds. All right, two more and we'll call it a day. So here, what weight corresponds to the top 15%? So here's my mean. I'm solving for a weight. I know that my top 15% would be the same thing as the bottom 7 or 85. Let me do good math. 85, right? Just 100% minus 15% gets me 85%. So I'm looking for the marker that would be right about here. Right, so here's my 85% that is to the below region, right? This would also be the top 15, right? So here's 15% that's in the above, and here's the 85 that's in that below. So using our older calculators, or the newer, we just have to specify the left-hand tail. So inverse norm, 0.85, 21.25, and then 2.2. It's going to pump out 23.5302 pounds. Okay, I figure you know the keystrokes at this point, so I'm just trying to move faster. Okay, last one, final problem. What is the IQR of weights? IQR. So the IQR is the Q3 minus the Q1. So here, again, here's my mean. I'm looking at how far away are those middle 50% of weights for 12-month baby girls. So I need the marker that's here, and then I just subtract them. So I know again that there's 25% that falls here and here. So to get each one, right, I do inverse norm to get this larger one. I would say 0.75, right, because there's 75% that's to the left. Mean of 21.25. Standard deviation of 2.2. That's going to give me 22.7339. Okay, and then I'll just give you the other one too. Try to move faster. So it's going to be 19.7661. The only thing that would be different would be plugging in a 0.25 right there. Okay, and then if we take the difference between them, we get to 2.9678 pounds. All right, so the range of the middle half of weights is almost 3 pounds, right? 2.9678 pounds. All right, that's it for today. Have a good rest of your day.